When we study nuclear physics, one of the key aspects that we have to deal with is radioactivity. If you look at all the nuclides in nature, any combination of of N and Z. Okay, each specific combination is called a nucleate, as you know. The overwhelming majority of nuclides in nature are not stable, which means they would decay into something else by emitting particles. This is called radioactivity. You have to deal with that. Okay, we usually don't deal with that in daily life because most of the elements that we deal with that are surrounding us are non-radioactive. They're stable, but because they're stable, we see them all the time. The unstable ones, many of them have already died. But when you study nuclear physics as a science, radioactivity plays an extremely important role. So let's take a look at radioactivity. That's the spontaneous emission of nuclear radiation. By radiation, I mean particles. So the nucleus is unstable, it emits some particles, becomes something else. Okay, the history in a very short account, it was first discovered in 1896 by Becquerel. And today, Becquerel is a unit of radioactivity. 1 becquerel, or 1 BQ, equals 1 decay per second. Okay, so that's SI unit, 1 decay per second. That's a very, very small unit, by the way. And when it comes to radioactivity, the most prominent names associated with it are the two scientists named Curie, Madame Curie and Pierre Curie. They did painstaking work and discovered two important radioactive elements previously unknown. One is called radon, Ra, and the other one polonium. This one, the reason why they call it radon is because it has to do with radiation. Polonium is associated with the country of Poland because Madame Curie was Polish. Madame Curie was one of the most important physicists of the 20th century, and she was also considered by many, including Einstein, as a saint of science because unlike many other people, unlike most of us, she studied science not because it brought her fame and glory and everything else, but at least partially because of that. She studied science just because she loved science. Most of us, even some of the greatest scientists, Einstein himself included, would welcome fame, would welcome fortune, in addition to the joy of great scientific discovery. But Madame Curie completely ignored those things. She in fact had a distaste for those things. She was only interested in physics herself, and that's partly what made her such a great physicist. In fact, she declined to apply for a patent for radon, the element that she discovered, which would have made her extremely rich. And her daughter also won the Nobel Prize in physics. In fact, there are two prominent physicist families in Europe around the same time, the Bohr family and the Curie family. Niels Bohr Sr. and his son Asia Bohr both won the Nobel Prize in physics. And then Madame Curie and her daughter. Madame Curie, in fact, won the Nobel Prize twice. It's incredible. Okay, now take a look at radioactivity. What kind of emissions are we talking about in spontaneous emission of radioactive nuclides? Well, basically there are three types discovered by physicists. Three types. We call them alpha, beta, and gamma. Okay, alpha particles, alpha emission. Basically, that's the case where the nucleus emits alpha particles. An alpha particle really is just the nucleus of the helium. It's got 2 protons and 2 neutrons. And the reason why you have alpha decay is because alpha particle, the nucleus of helium itself, is a very stable combination. Remember in that chart that we saw a minute ago? Okay, on the chart of stability, here's helium. Here's the alpha particle right here, helium-4, 2 protons, 2 neutrons. Okay, it's got a spike in the bonding energy. It's extremely stable. Okay, so shouldn't be surprised. That's alpha decay. And you also have beta decay. Beta decay has 2 types. In the first case, a positive charge is emitted. In the next case, a negative charge is emitted. both charges have the same exact mass. The negative charge one is really just an electron. Okay, the positive charge one is curious because it's got the same mass as the electron. It looks every bit like the electron behaves, except it's positively charged. We call it a positron. Positron. And then the third type is called gamma decay or gamma radiation. In this case, only a beam of light is emitted, or photons are emitted. These photons have extremely high energy. We call it gamma rays. It's charge neutral. How do we tell the charge? Very simple. We have a radioactive source, right? And we expose it to a magnetic field. So a beam comes in. If the beam deflects this way, according to Lorentz force, Q V cross B, V goes this way, so B goes into the paper, so V cross B points this way. So if it's positively charged, the particles will go this way. Negative charge goes that way. Charge neutral, don't get deflected at all in a magnetic field. That's how we tell whether these beams are positive, negative, or charge neutral. That's physics 1C, of course. Now, let us consider how the number of radioactive nuclei in a sample would change over time. This N is the total number of radioactive nuclei in a certain sample. Okay, this is a number that still remains active, which means it hasn't decayed yet into something else. Once it decays, we say it dies, it becomes something else. We don't count it anymore. So let's say at t equal to 0, I start with this many active radioactive nuclei. As time progresses, they start to decay and decay and decay. So once something decays, we do not count it anymore, so the total number of active radioactive nuclei will start to decline over time. Now, let's consider these two possibilities. Here we have a straight line decay, so dN over dt is a constant. So the rate at which the radioactive element die is a constant. And here you have a case like this. It's more some sort of exponential decay, so that the number of radioactive elements, active ones, do decrease over time, but they do not decrease over time in a straight line. In fact, the rate of decay slows down as time progresses. So which one do you think makes more physical sense? Well, to understand this, we have to look at the mechanism behind nuclear decay. If you look at a certain nucleus, it's radioactive. You just never know when it decides to decay. You just never know. Some takes long time, some takes short time. There is some sort of average. Okay, if you look at a whole bunch of them, you can say on average how long does it take for them to decay and so forth. But if you focus on each one of them, you just never know when it's going to decay. Let's say within the next minute, let's say I have a whole bunch of them. Okay, I have 1 billion of them. Let's say within the next minute, there is a 50-50 chance for each of these to decay. All right. So I start with 1 billion, right? Right. 1 minute later, how many do I get? I get 500 million, right? Now, a minute later, I get 500 million. Now, these remaining 500 million nuclides, what happens to them? Again, with every passing minute, there's a 50-50 chance for them to decay. So therefore, after another minute, half of those guys would decay, so that's 1/4 times 10 to the 9. That's how much is left. And then again, 1/8 times 10 to the 9, and so on. So if you look at how many of them died or how many of them decayed within the first minute, that's 500 million. But within the second minute, only 1/4 of them died. 1/4 of the original one died, right? Because you start with a smaller number to begin with. So the decay rate actually drops from 500 million per minute to 1/4 billion per minute to 1/8 billion per minute. This curve makes more sense. See that? Okay, now what is the exact mathematical expression for this curve? Turns out it's rather simple. Let's see. Let's consider a time dt. During that time, this many nuclides went through a decay process. In fact, dN is the change in the number of remaining radioactive nuclides. So dN is a negative number. Okay, it is a negative number. We want to know what this is proportional to. First of all, it is proportional to the number of remaining radioactive nuclides. Okay, because if you double the number, then you will double the total number of decay, because then you basically have 2 samples instead of 1. Each sample will have, say, 100 decays. Then with 2 samples, don't you have 200 decays, right? So the proportional n. It is also proportional to what? to the time interval. You give it longer time interval, more will decay. If in the example that I gave a minute ago, 1 minute, there's a 50-50 chance of decay. What if it's 2 minutes? Then the chance of decay will be greater, right? Because if you didn't decay in the first minute, there's still a 50% chance you're going to decay in the second minute, and so on. So it's also proportional to dt, right? But that's not an equality. To get an equality, we must add a constant to balance the two sides. dn equals a negative constant times n dt. This constant we call decay constant lambda. Why do we need a constant here? Because first of all, without this constant, two sides cannot possibly be equal because they don't have the same dimension. Okay, this is n, but there's a dt here. So this constant must have a unit of what? 1 over time, right? To balance the units, that's one thing. Another thing is that constant depends on what? How fast this decay process is. Is this a slow decay element or fast decay one? It makes a difference in lambda. All right. With that, we can easily integrate both sides and find n as a function of time. Before we do that, let's just move n to this side so we separate the variable. So I have dn over n equals negative lambda dt. All right. Now let's integrate between 0 and t. Between 0 and t, n changes from the original value n naught to the final value n. The left-hand side is a natural log of n over n naught. The right-hand side is just negative lambda t, right? And you raise both sides to exponential, you get your result. The result is n equals n naught e to the negative lambda t. Okay, what is the physical nature of lambda? If lambda is large, it's going to decay pretty fast, which means it's a fast decaying element. If lambda is small, it's the other way around. When it comes to how fast something decays, we usually do not use this constant lambda. Rather, we use something more straightforward to understand, and that is the so-called half-life. T1 half. What's T1 half? Suppose you start, like the example that I gave, 1 billion active radioactive nuclides. After a minute, half of them died. So the time it takes for half of the sample to decay is 1 minute. That 1 minute is called half-life. Okay, in the next minute, what happens? You start with half a billion, right? You could end up with 1/4 billion because again, 1/2 of the sample died. So 1/2 of half a billion, that's 1/4 billion, and so on. So what's half-life? It's the time it takes for half of the radioactive sample to decay, right? This n, as a function of time, is a curve like that, That's a curve like that, right? If I plot this curve, I start with n naught, then I find half of that n naught. So this is a billion, this is half a billion, right? So I found half a billion here. I draw a line parallel to the t-axis, and I find the corresponding time. That is the time it takes, okay, going from 0 to here. That's the time it takes for the sample to drop from n naught to half of n naught. By definition, this is T1 half. Okay, that's T1 half. T1 half. Next, you start from half of n naught. I want you to drop another half to 1/4 of n naught. So you go from here to there. What's the time interval between here and there? That is again T1 half. So here is 1 T1 half, here's 2 T1 halves, and then 3 T1 halves, and so on. And after n T1 halves, what's the sample that still remains? Well, you have n equals what? After 1 T1 half, you have half of left. After 2 T1 halves, that's 1/2 squared. So after n of them, this is how much you have left. Okay, so if 1 minute is the half-life, what about 10 minutes? 10 minutes into the counting, how much do we have left? How much of that 1 billion initial numbers do we have left? It's 1 billion times 1/2 raised to the power 10. That's how much you have left. Not much. Okay, so it's very easy physics. And this T1 half is related to lambda. The longer T1 half is, the slower the decay, therefore the smaller the value lambda. So they should be inversely proportional to each other. Let's see here. Let's find T1 half from this expression, okay? Set n to be 1/2 n naught. Isn't that what I want? Half of them decays. Okay, so put this in here, so I get 1/2 n naught equals n naught e to the negative lambda t. But that t is by definition T1 half. Okay, at t equal to T1 half, n becomes 1/2 n naught. move this, cancel that n naught, and then you take the natural log of both sides. Natural log of 1/2 equals natural log of e to the negative lambda t1/2. Okay, so clearly you find that that's 2 equals lambda t1/2 natural log 2. Flip it over, right? So t1/2 equals 1 over lambda natural log 2. That is how you find one quantity from the other. This is called a decay constant, and this is the more physically meaningful quantity called half-life. Half-lives can range from very small fraction of a second to billions of years, depending on which element we're talking about. So in the next lecture, we are going to take a closer look at the 3 different modes of radioactive decay: alpha, beta, and gamma, and we'll go from there.